It is also important to understand that a router is not an entity that works in isolation. It works in conjunction and through the collaboration of other routers in the network. For that, router performs a very important function called the routing operation. Routing algorithms form the heart of routing operations. In this module, first we'll understand what is the relationship between routing and packet forwarding. We'll understand the topology of routers through a graph abstraction, and then we'll ask the key question about the usage and the necessity of routing algorithms. The reference for this module is by Quiroz and Ross. The routing process is a precursor or a prerequisite to forwarding because the routing algorithms perform end-to-end path discovery for a given network. When a packet arrives in real time, it is processed according to the routing information which is pre-stored and the IP address that is carried in the incoming IP datagram. Now, we can also establish a visual relationship between routing and forwarding through this figure. You can see this example topology. Here we see that the routing algorithm creates the routing tables. The routing tables are established through the mutual cooperation of the routers in a given topology. So when a packet arrives, its IP address is compared and consulted with the stored routing table. The topology of the routers could be understood as a graph, which has edges and vertices. So if we represent a graph G with the number of nodes or the vertices as n and the edges as e, n would represent the number of routers for the given topology that comprises u, v, w, x, y, and z, and their edges are shown with their associated costs. We can see that the set of links are actually represented through the relationship between the two nodes which they connect. For example, the edge with the cost 5 in this figure is between node u and v, and so forth. What is this cost? Cost is the effort or the monetary investment needed to move from point A to point B. In terms of routing, it is the routing cost that is end-to-end based on the aggregate or summation of the links associated with that path. For the sake of simplicity, we can represent the same graph that we've seen using costs of unity. In that case, for all the edges that we see, the cost of every link is going to be 1. But in reality, more complex representations of cost exist. For example, costs could be associated to bandwidth. That is, a high data rate link has lower cost, and a lower data rate link has high cost. Similarly, a relationship could be established with the congestion that builds on a certain link. If the link is overly congested and is congested too often, then it is given more cost. And for a loosely congested or a lightly congested link, the costs could be low. As I said earlier, the cost of the overall path is the linear summation of the costs of their individual segments or links. So routing algorithms attempt to answer the fundamental question, that is, for a given topology, for two arbitrary nodes such as u and z for this particular module, what is going to be the least cost path and how it is going to be determined. The routing algorithms attempt to answer this question through various algorithmic implementations.